Yield lines, special cases. This video will deal with rectangular slabs with 2 point supports and 2 simply supported edges. So we have a rectangular slab with 2 point supports and a simply supported edge at size B. B is bigger than A. We will use the method of yield lines to determine the maximum bending moment. First, we look up the axis of rotation, which is of course here at the end support. The axis of rotation to the point support is situated like that, but the angle can vary. The same is for the other side, but because of symmetry around the YY axis, we know that the yield line must be here in the center. It must start there somewhere. So this is angle and this angle are the same because of the symmetry on the YY axis. The yield line must be situated around this. It's between those two, but we must optimize the angle, alpha and beta, to find the direction of alpha. You need to optimize alpha to find the direction of the yield line, and beta to situate, in fact, this point. You have the same on the other side. So also with alpha beta, and because of the symmetry in the YY axis, this alpha is equal than this beta is equal than that. And then we see that the yield line starts at the crossing and stops at the end of the slab, of course, and then you have those 3 yield lines. So we have 2 parameters, alpha and beta, who can determine the position of the yield lines. And this, we call this the x1, which is the tangents of alpha, and x2, the tangents of beta. We will use alpha and beta in degrees and not in radians. We need some geometric quantities because we have to calculate the work done by internal external forces, so we'll need some parameters to put in. This is the parameter that I've chosen. We will go through it one by one. We can now express all parameters in function of x1 and x2. And we use a parameter mu, which is b over a, but this is not an optimization parameter, but just a shape parameter, so that we can so that we can use the different formulas for other rectangular slabs. Cosinus alpha in function of tangents alpha gives you a very easy expression in x1. The same for sinus alpha. The tangents gamma is equal to the cotangents of alpha plus beta is given by this formula, and then you can write it directly in x2 and x1. And the tangents on alpha plus beta is, of course, this. That's the known tangents formula of summation. The summation of a cosinus, you can also express it in or work it out like it's shown here on the slide. And the cosinus alpha and beta and the sinus alpha and beta is or it's expressed using the previous formulas. As for it's easy, it's just S4 divided by B over 2 is the tangents of alpha plus beta, and the tangents of this angle is the same as this angle. And this can be expressed in x2 and x1. S6 is x6. We will use the cotangents rule, which is the base S2 divided by the summation of the cotangents of the 2 adjacent angles. And then you can also arrive at this expression. S1 in this triangle, it's easy. So the cosine of alpha plus beta is equal to S3 divided by S1. We continue with S2. S2, we will use this triangle, and then we have an easy expression of S2. The tangents of alpha plus beta is, of course, S4 plus A divided by S3 plus half B over 2, this triangle. And S3 equals, from this expression, we can find S3. And A1 is S3 times tangents alpha, and you also can have this expression. So we can continue to express every variable in function of x1, x2, and mu. For H3, again, the cotangents rule is used, but you see it's getting more and more complicated. The S7, which is this, which is important, the S7 to calculate the virtual work done or the work done by the internal forces. So it's equal to this expression. And S5, again, the cotangents rule. Now that we have all the different geometric parameters, we can start with by calculating the maximum bending moment in function of alpha and beta and mu. And we start with the work done by the external forces, E over delta Q. It's equal to this triangle here, which is H1 times the base is 2S3 plus B divided by 2 and multiplied by the mean deflection, which is H1 divided by 3 because it's triangle. But we must subtract this portion which is outside the triangle. So this is the portion we subtract. It is, for instance, A1 times S3 divided by 2. And we take the maximum deflection. It's A1 divided by H1. And that we take 1/3 because this is the triangle. That's what you get here. We do the same for this triangle, and we subtract those two, and we do the same for this triangle, and we subtract this and this value. So in fact, it's quite straightforward. You can then try to substitute every variable in it, but that will give you a very long formula. So I just simplified a little bit by this equation. The work done by the internal forces, it is this yield line projected to that axis of rotation. So this is B times the angle of rotation, delta over H1. So that's this term, B divided by H1. And then we got this yield line projected on that axis of rotation. So that means S7 divided by H3. And we got that on this side, and this, and on the other side. So that's D. So now we know when E is equal to D that the bending moment M is a function of alpha and beta and mu, because mu is B over A. And this expression is equal to Q times E over D. We have to satisfy some conditions. Of course, H1 must lie inside the slab, so H1 is smaller than A, and A1 must be positive. The crossing must be inside. The crossing of the yield lines must be inside this slab. And of course, alpha plus beta must be smaller than 90 degrees. Otherwise, it will not lead to any sensible yield line position. H1 smaller than A means that x2 must be smaller than certain value of x2, and this certain limit value is given by this expression. You just have to fill in the x1 in this expression, and then you will find this. So H1 is smaller than A when H2 is bigger than H2M, given by this expression. A1 must be positive. This means because A1 is equal to this formula, and then you see it is only possible that it's only possible when A1 is positive, when X2 must of course be bigger than 1 over X1 because of that. So this is the formulation X2N is then equal to 1 over X1. What does this mean in practice? Those three conditions, you can plot them on a curve. This is alpha in degrees from 0 to 80 degrees. And this is the value of X2M, which is the condition H1 smaller than A. It means that every value combination of alpha or beta must be on the left-hand side of the curve. I'll give you an example. Suppose that we have a square slab, so beta or mu is 1. Then you have the red curve. So that means that only the values to the left of this curve are valid values in function of alpha, and this is beta. The line that you see here, this line, it's x2n, it's x2n, that is alpha 1 must be positive. So everything on the left-hand side is okay. So again, we will see it now on this graph. And give an example, we have the combination alpha and beta and mu. So for instance, for alpha 50 degrees and beta 30 degrees, then we have this yield line pattern for a square slab. Mu is 1. And then you will see for mu is 1 that x2 must be on the left-hand side of this curve. So this, when alpha 1 is 50 and alpha 2 is 30 degrees, it's on the left-hand side, and it's below or on the left-hand side of this curve x2n, meaning that A1 is positive. Of course, you can see it here. A1, this is A1 is positive. When you are on the other side of this line, for instance, for 70 degrees, then this will be negative and fall outside the slab. So this is a point which is okay. Take now, for instance, the point 60, 50, and 1.5. So it means that for beta equals to 1.5 A, so mu is 1.5, you have the blue dotted line. We must be on the left-hand side of it. Then we are here. So we are on the left-hand side, but we are on the right-hand side of the curve x2n. So A1 is negative, and you can see it very clearly. A1 here is negative, so this is not okay, and it is not good. And then another example, for instance, for beta equals mu equals 2, you got x2m, this curve here, the black dotted curve. We must be on the left-hand side of this curve. And you see that, for instance, 2022, and this is 20 degrees, and mu is 2, that this pattern is okay. So to make our life a little bit easier, we should be at the left-hand side of this curve, then everything is fine. But this limit of validity is depending on the factor mu. So we chose now that we will work on this area. So it means that we have a good chance that the values that we find for the optimization is within the conditions that we have put down, because we are on the left-hand side of this. So it means A1 is always positive. So we will try to work in this region. Doing so, alpha from 0 to 40 and beta from 2 to 40 degrees. And we have chosen mu. This is just a parameter for the shape. It's 1.5. So B is 1.5 A. When we do this, we can draw different curves in function of beta, and you see that they reach all a certain maximum. But this maximum is is um, uh, it's limited in a certain range of alpha. So we will now um, uh, take this region where they all reach a certain maximum, and when you blow this up, when you make it bigger, then you see from this area from alpha from 15 or 16 to 30. So it's this from there to there, and then from the bending moment 3.3 to 3.4, you see that's in this limited area. So this is that. Then you see, if you look in finer for alpha, for beta, beta at 21, 22, 23, and so forth, you will see that you gradually reach a maximum, and then for instance, the black curve going down again. So we can be confident to say that the maximum is found as 23.5, 24, and 1.5. So that's this point there. Of course, the scale to calculate m, the scale q8 squared is taken as 25. So maximum bending moment, you can calculate now maximum bending moment in function of alpha and beta for each mu. And it's a different case. Mu is 1, it's a square slab. Mu is 2, it's a rectangular slab, and so on. So for each mu, you can redo the exercise, what we've done just now for 1.5, and calculate alpha and beta. And this is the corresponding maximum bending moment. We check that all those values are valid. And when you plot it more or less on this validity chart, which is alpha 1 and this is alpha, sorry, this is alpha and this is beta, then you will see we are all in the region that it is okay, that is fine. So all those parameters can be right. Now, the next step we are doing is we are saying that the maximum bending moment is equal to Q times AB, that's the total load on the slab, divided by a factor K. That's easy to work with. So we calculate the factor K for each maximum bending moment, and for each mu, we can calculate K, and we can plot it now, those values. By doing so, we can fit those different variables for mu between 1 and 2. Otherwise, when you go further on, it will be another calibration, but most of the time, it's unrealistic when mu is bigger than 2. So for mu between 1 and 2, you can have a regression, which is given by this formula. So this means that the maximum bending moment is now a function of mu alone. It's QAB divided by K in function of mu. B is, of course, mu A squared. So you have now this expression QA squared mu divided by K mu, and then we fill it in. So now we have a very usable formula, closed formula, to calculate the maximum bending moment of a slab of this situation. For a square slab, for instance, then mu is 1, and when mu is 1, we have m max is q8 squared divided by 8.25. We can now give an example of a slab 6 meter wide, 4 meter in the other direction, 2-point supports and simply supported on one edge, a load of 20 kilonewton per square meter. So A is 4 and B is 6 meters. So this means that mu is A divided by B is 1.5. It means that from our graph that alpha is 23.5 degrees and beta is 24 degrees. So this is 23.5, this is 24. And the K factor for 1.5 is equal to 10.9. So the maximum bending moment is QAB over K. So it's 20 times 4 squared times mu divided by 10.8, because B is 8 times mu. And we have a bending moment of 44 kilonewton meter per meter, so in X and Y direction. And the yield light pattern is drawn like this.